Okay, so this is where we left off on Monday's lecture, so I thought I'd run through this argument for those of you who want to see it ahead of time. So here we're going to consider the following relation on the integers. So our objects are integers, so x and y are going to be integers. That's what this says here. So U is going to be the set of pairs x, y, so that both are integers, and their difference is even. Okay, so another way of writing this is these are the set of all x, y, such that x and y are integers, and x minus y is in the evens. That was one way we wrote the evens, the multiples of 2. Or another way of writing this could be xy such that x and y are integers, and 2 divides x minus y. What's another way of writing this? We could say xy such that they're integers, and x minus y is equal to 2k for some k in the integers. Lots of different ways of saying the same thing. So let's look at whether it's reflexive. Remember, we start reflexive by saying that, just make sure that my microphone is on. I can't tell. Hopefully it's on. We start with reflexive by starting with an element inside of the set on which my relation is defined. So since here we have U is a relation on Z, we take an element of the integers. So we take an x in the integers, and we want to know whether, we ask, if x minus x, or if x comma x, I should say, is in my relation U. Well, how would it be? What's the condition? The thing that we want to look at to decide whether or not x comma x is in U is this difference, the first coordinate minus the second coordinate. So in this case, the first and second coordinates are the same. That's going to be 0 no matter what. And I notice that 0 is 2 times 0, so it's in the even integers. And so that tells me that x is in the relation U. Okay, so and that tells me that U is reflexive. So no matter what integer I start with, I can always pair that integer with itself. I can always pair that integer with itself. Why? Because the difference of the integer and itself is 0, which is a multiple of 2. Okay, so it is reflexive. How about symmetric? How do we start symmetric? Symmetric says anytime xy is in there, then yz is there. So now we start differently. So we suppose that we have an element inside of our relation, and we want to know whether the ordered pair in the opposite order is in our relation. So what we're going to start with is what we know. We know because xy is in the relation that x minus y is a multiple of 2. So let's just start with that. So we've got x minus y is equal to 2 times k for some integer k. And what are we interested in? We're interested in the opposite order. So if we look at y minus x, that's going to be minus x minus y, which is going to be minus 2k, which is 2 times minus k. And since minus k is an integer, this is still an even number. So that tells me that y minus x is still in 2z. And that tells me that yx is in my relation. And that tells me that U is symmetric. And finally, transitive. How does that start? This time we start with an x and a y, and then starting from y and going to another z, we assume those two ordered pairs are in my relation, which is called U. And I write down what I know because of that. So x minus y is equal to 2k, and y minus z is equal to 2l for some k and l inside of the integers. Now, if I look at x minus z, then I know that x minus z is equal to x minus y plus y minus z, which is 2k plus 2l, which is 2k plus l, which is again inside of the even integers. And so what I see is that xz is in my relation, and thus u is transitive. So this is our first example of one that is reflexive, symmetric, and transitive, and therefore, thus, overall, u is our first equivalence relation. So it satisfies all three conditions. So what I'd like you to consider doing now is to consider doing the same thing. This is a copy of one of the page 8. Notice I've amended it to look at not u as we had it before, where the difference was a multiple of 2. Now I'm saying, what if it's a multiple of n for some fixed n? Okay, so I invite you to show that the argument above works exactly the same thing, that u sub n is an equivalence relation. Okay, all right, enjoy.